So we've talked about Maclaurin and Taylor series. We're just going to define the concept of a Maclaurin polynomial and a Taylor polynomial. It's a fairly simple idea. A series of course goes, from some starting point out to infinity. It goes up to powers of infinity. With a polynomial, this is what the definition of a polynomial really is it's just a finite number of integer powers. So what we're doing is we're taking the series and just cutting it off at some power. I've alluded to this before. Sometimes we ask for the Taylor series or the Maclaurin series up to, let's say, degree 4. So we're going to formalize this idea and define m sub n of x as the Maclaurin polynomial for f of x up to up to a degree of n, and similarly we'll define Tn of x as the Taylor polynomial for f of x up to degree n, where we're going to assume some center c. I'll just give you a very simple example. We've seen already that the series for cosine x is defined this way, and that comes out to 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, and this goes on forever. If I ask you for, let's say, just m4 for cosine x, what you would do is you would just stop right here. You'd get up to the power 4, and you'd just stop. So m4 for cosine x is 1 minus x squared over 2 factorial plus x squared over 4 factorial. There's no dot dot dot. We just stop when we get to power 4. This turns out to be fairly useful for coming up with approximations. As we talked about, just as we did in Calc 1, where we used a linear approximation, we can use an approximation up to any degree that we want. And this is sort of how we refer to this. It may not surprise you to learn that the linearization of x that you learned about in Calc 1 is just equal to t1 of x for some center. Of course, you always chose what the point was that the point of tangency was. It wasn't always 0, that's why I'm writing this as t, but t1 is just a linearization. And here what we have is sort of a 4th degree polynomialization, m4. So let's see how we use this, and I want to make a couple of points with the next example. So let's use f of x equals e to the let f of x equal e to the negative x squared. What we want to do is use m4 to find the approximate value of the integral from 0 to 1 of e to the negative x dx. So here's what we do. First of all, let's find m4. Now, it might be tempting, as I know many people do, because I know a lot of math students like formulas. I don't know why. I love math, and I never like remembering formulas. I know that we all know the formula m of x equals, at least we all know it by now because we just learned it in the last hour. M of x is just equal to that. And it's tempting to say, oh, all right, let me just find the first 4 derivatives of e to the negative x squared. This is going to be an enormously annoying chain rule problem to do, because by the time you've taken this derivative, you've now got a chain rule problem and a product rule problem. So for the second derivative, you're going to have to do the chain rule and the product rule, and it's just going to mushroom out of control. It's not fun to do it this way. So the thing to recognize is that e to the x, we all know this now because we just learned it in the last hour, is equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus dot dot dot. So if I want to find e to the negative x squared, I can do this like a composite function. Every place I see x, I'll just replace it with negative x squared. So that's going to be 1 plus negative x squared. I'm replacing that x with negative x squared plus negative x squared squared over 2 factorial. I did it to replace it in that term, plus negative x squared cubed over 3 factorial. It turns out I'm not going to need that last term, but just write it in there because it's there. So let's simplify this. This is going to equal 1 minus x squared. Negative x squared squared, since I'm squaring that minus sign, that's going to turn it positive, so that's going to be x to the 4th over 2 factorial is just 2. And since I'm only being asked for m4, I can just stop there. I can just say m4 of x is equal to that. That's m4 for the function e to the negative x squared. And it turned out I did not need to use this because I'm only going up to power 4. Had I used it, I would have simplified that. That would be negative x to the 6th over 6. So we now have m4. the idea is that this is a pretty good approximation of e to the negative x squared as long as we stay pretty close to 0. So let's see, how can we use this? So actually, let me just pause for a minute. The first point here, which would apply even if we weren't doing this kind of problem, is how to use composite functions with series. In other words, if you know the series for some function like e to the x, sine x, or cosine x, you can use those series in a composite way like this by just replacing. If you have an inner function, just every place you see an x in the original series, just replace it with whatever the inner function is. The next thing to understand is that this function is a reasonably good approximation of e to the negative x squared as long as we stay close to 0, and therefore we should be able to find an approximate value of something that uses e to the negative x squared by using m4 as a stand-in. Let me draw this. One thing, you may or may not be familiar with this if you've taken a stat course, but e to the negative x squared is basically the shape of the bell curve, the shape of the normal distribution. You have to multiply it by something to make it the density function for the normal distribution that you would have learned about in stat. And by the way, if you don't know what a density function is because you didn't take stat, just ignore that comment. But if you did take stat, you know what a density function is, and you know that this is the shape of a normally distributed random variable. So the this is a fourth degree function with a positive leading coefficient. The coefficient of the highest power term is positive. So what this actually looks like is kind of like this. It's going to look sort of like this. So as you can see, it goes pretty far off the rails from the bell curve, but as long as I stay in between these two dotted lines, saying pretty close to 0, it's actually not bad. It's actually not a bad approximation of the shape of the curve as long as I don't go too far out toward either side. So the point is that what we can do is if we want to find the area under the purple curve, we could instead just find the area under the blue curve, and we'd get pretty close to that area. That's the whole point of having these approximation functions that we're constructing. So and by the way, the reason you wouldn't just integrate e to the negative x squared directly is you can try it, but it's provably true that there is no elementary antiderivative for e to the negative x squared. Which is not to say there isn't an antiderivative, it just can't be expressed in any convenient form. It can't be expressed like using powers of x or sine x or e to the x, or using only those types of expressions. It requires much more complicated expressions to describe what the antiderivative is. Functions that we can write as sums, differences, products, quotients of the basic functions like like power functions, roots, sines, cosines, tangents, or exponentials, we call those elementary functions. So there's no way using any combination of those to write the antiderivative of e to the negative x squared. So instead we're going to approximate it. The observation here is that the integral from 0 to 1, use green for this, the integral from 0 to 1 of e to the negative x squared dx, which we cannot calculate directly, is approximately equal to the integral from 0 to 1 of m4 of x. Why? Because that's the whole point. We created m4 to stand in for a function that we don't want to deal with. We created this approximation of it. Well, that's going to be equal to the integral from 0 to 1 of 1 minus x squared plus x to the fourth over 2. And how easy is that to find? That's just going to be x minus x cubed over 3 plus x to the fifth over 10 from 0 to 1. When I plug in these the term 1, when I plug in the 1, I'm going to get all the positive terms. When I plug in 0, I'm just going to get 0. So this is going to be 1 minus 1/3 plus 1/10. The common denominator here is 30, so that's going to simplify to 30 minus 10 plus 3 over 30, and that comes out to 23 over 30. Now, how good of an approximation is this? I mean, hopefully you understand that what we did was I found the area under this blue curve. I didn't find the area under the purple curve, but because of the way I constructed the blue curve, it's pretty close to the purple curve as long as I don't get too far from 0. So how close is this? 23 over 70 is approximately equal to 0.77. If I ask Wolfram alpha to give me the actual value of this, which it's not doing directly, it's just doing it by, by dividing the region into, let's say, 10 billion rectangles and adding them up, getting sort of a very large Riemann sum, that comes out to approximately 0.75. So that's not bad. By integrating something that was really easy to integrate and was designed to be pretty close to the original function, I got about 2% away. So that's a pretty good approximation. That's one of the things that you can use these Maclaurin series for.